Welcome to the third and final installment of TA Instruments Strategies for Better Thermal Analysis Data. In our final segment of the series, we join Dr. Jason Senger, who will provide tips on general data presentation and analysis.
Hello, I'd like to welcome you and thank you for joining us on this third and final segment on strategies for better thermal analysis data from TA Instruments product specialists. Our segment today will discuss general data presentation and analysis. So I'd like to start out with some tips on data reduction and presentation. We'll look at some proper scaling for normalized sensitivity. We'll also take a look at some derivatives and appropriate use of derivatives. And we'll also take a look at some overlays and inlay plots. So here you can see a modulated DSC run that is opened up in Universal Analysis. Now by default, Universal Analysis will maximize the scale for each variable on each separate axis. And so in this case, you can see in the red curve, it looks or appears as if there are transitions that are much larger than they are in relation to the other two variables that show up on that plot. So what you can do is then go to the rescale menu and choose same scale. And in this particular case, when we plot everything on the same scale, it equalizes axes 1, 2, and 3, and you start to see the data presented in its more normalized form such that each transition is comparable to the other. So now it shows you that the total heat flow curve here in green is equal to the sum total of both the red curve and the blue curve. Now in trios it's a little bit different, but you have the ability to plot all three variables on the same axes. So here you can see in trios we have the variables menu open, and we are putting the non-reversing, reversing, and total heat flow curves all on the Y1 axes. When you plot this particular data set, you can see that, again, all three variables are on the Y1 axes, and you normalize your three plots so that none of these transitions are out of scale in relation to the other two. Now, derivatives are used quite a bit in TGA, but derivatives can also be used for other things. So in Universal Analysis, what you can see is that when you are in the Signals menu, you have the ability to look at a particular variable and change that variable to the derivative in respect to time or respect to temperature. You also have some functionality in terms of second derivatives, but they're not as commonly used as a first derivative curve. And so in the Signals menu, you have the ability to switch that in Universal Analysis. In Trios, you actually have the ability to apply a derivative with respect to time or temperature directly from the plot. So there are drop-down menus. There are also options in the right-click menu option. So like I said, that TGA typically is the most common use of derivatives. Here you can see a weight loss curve in the TGA in green. And we are also plotting the derivative of that weight loss in blue. And so the derivative in this case it gives you a couple of different benefits. One is that you do see small or subtle changes or small or subtle weight changes in your derivative, and they typically show up as a small bump in the derivative curve. You can see that at lower temperatures. But the primary use for derivatives on a TGA plot would commonly be allow you to choose your points of analysis. So typically you would look at a weight loss curve from one plateau region to the next, or from one derivative minimum to the next derivative minimum. And it will allow you to much easier or very objectively determine a weight change from point to point. Now, derivatives can be used in DSC. They're not as common as TGA, but in this case, you can see that the derivative curves are accentuating the change in baseline shape that surrounds a glass transition of this particular data set. You can see that in the heat capacity curve in green has a subtle baseline shift, and you can use an analysis tool on that particular baseline, but the derivative curve actually shows you a peak. So in some cases, it's just much easier to be able to see a peak and recognize where the glass transition might exist looking at a peak rather than just a subtle baseline shift. Here is another example where, again, there are three curves here. There's a heat, cool, and a reheat. And you can see that on the green curve, again, a very subtle baseline shift. So it's not as easy to detect small shifts in these baselines. But clearly, by plotting the derivative curve here in blue, you can see that there is a significant difference in the temperatures at which this glass transition exists, or where this baseline shift exists. So the first, second, and cooling curves are all shifted from one another, and the derivative also gives you some scope of the overall width of that glass transition, such that it's nearly 100 degrees wide in this particular case. So overlay plots are one way that you're going to be able to compare various data sets. Maybe it's a comparison of a variety of different formulations. In this case, you can see that we're actually plotting a variety of indiums at different heating rates. So it gives us some good comparison, somewhat of a normalizing of the various indium melts at different heating rates. You can see that at slower rates, it's a much smaller peak. At fast rates, it's a much larger peak, even though the energy is the same. But overlays are really going to be a powerful tool when you're trying to present this data or show how materials might be trending in one way, shape, or form, or how different formulations might compare to the next. In universal analysis, in order to create an overlay, you will have to open up all the files that you want to be placed into that overlay. And then the easiest tool would just be to choose the auto overlay function, and it will then guide you in terms of the various files that you want to put into that overlay, the variables that maybe you want in that overlay, and then it will guide you in terms of auto color, auto line style, so that when you open them up, they may all have a different color, such that you can then differentiate them. So once you create an overlay in universal analysis, it's somewhat set there, so you don't have a lot of in terms of a functionality for changing variables. So you want to make sure that you get your variables set correctly before you create your overlay. Now, in Trios, you actually have a much easier method in terms of creating an overlay, and you have a lot more flexibility in terms of manipulating it after the fact. So what you can see here is that on the left-hand side, we have our file manager. Again, the particular files that we want to be put into that overlay need to be open. But once you do that, you create a new overlay document. You can see that listed at the bottom of the list in the file manager. But then you have full functionality in terms of dragging data sets or segments or steps from your open files into your overlay. So you actually have a lot more flexibility in terms of creating the overlay. Once you create it, you, again, have more functionality in terms of selecting particular variables. You can change variables. You can change your auto color, auto line style very easily in Trio. So there's a lot more power there than what we had in universal analysis. So in this particular case, you can see that we actually have the ability to plot multiple data sets or multiple instrument types on one overlay. And so in this particular case, we actually see a weight loss curve that was most likely collected from a TGA, and a heat capacity curve, which was collected from a modulated DSC experiment. So two separate instruments, two completely separate types of data sets, but the one commonality in this case is temperature. And so because they both have temperature as a x-axis, you have the ability to plot an overlay of those two particular curves. And so it gives you the ability to compare the transitions that might exist in one form versus another. Is a weight loss in your TGA showing up as a transition in your DSC, or vice versa? And so you're not just limited to TGA and DSC. Obviously, you can plot TGA and TMA, and anything that has a common temperature scale, you're going to be able to create an overlay of those particular data sets, which will then allow you to present data to someone else. Now here is an inset view, and you can see that the inset really the power there is more or less just being able to present it to someone and pull out pieces of information that may be overlooked or overshadowed by other transitions that exist in that particular data set. So here you can see the glass transition of this PET is very detectable, but it's possible that you could have a glass transition or a baseline shift or a small transition that is so small in relation to the cold crystallization and melt or other transitions that may exist in that particular data set that an inset view allows you to zoom in on that specific section. So here we've zoomed in specifically on the glass transition for this PET, and it gives us a clear picture of what's going on in that particular region. Now, obviously, you've got a variety of other options that exist to format that curve, whether you want analyses to show up on the inset portion or just on the curve itself, or if you want borders and arrows and so forth. So there are quite a few options, but the power here is really being able to zoom in on something or pull something out of your data set and present that to someone effectively. Now, those were all just tips on presenting your data. Now, once you've collected it and you want to actually associate those particular transitions with something, that's really where the key to analysis comes in. So in this next section, we're going to look at correlating the data that you've collected and presented and analyzed, and compare it to correlate it to a particular structural property. So here is a variety of TGA type experiments. So we can see that we're looking at weight loss curves of a variety of common polymers. And you can see that we have a ramp, a 20 degree a minute ramp from room temperature up to, let's say, 1,000 degrees, or in this case, we're going up to 650 degrees. At that point in time, we're actually switching from an inert nitrogen atmosphere to and we'll call it an oxygenated atmosphere with air. Now you can see that what we're looking at in this particular case is weight loss, but it gives us an idea of the thermal stability of these particular polymers. So they all have a temperature at which they start to degrade even in that inert environment. And that particular temperature is really the breakdown temperature of those polymers. So that's your thermal stability component of those materials. Now, you can see that some of the materials break down in one single weight loss. They just break apart into much smaller pieces, and it's a very simple breakdown process. Some of them are more complicated and have multiple steps to them, and some of them leave behind an organic residue or a carbon residue, and that's really where the switch to air is your benefit. And so you can see that at 650 we switch to air, you introduce oxygen, so that at those temperatures any organic material that exists is then breaking down into CO2, CO, and so you can see a secondary weight loss that occurs after that gas switch. Now, thermosetting polymers are cross-linking materials. It's your common epoxies, your 5-minute epoxy, 10-minute epoxy. And it's really just a mixture of component A and component B, and in some cases, when when you're talking about a 5-minute epoxy, you mix the two parts together, and there's enough interaction, chemical interaction between those materials at room temperature for them to start cross-linking. So you start binding these chains or building these chains and creating a structure that goes from a mobile liquid, a mobile gel type structure into a very rigid cross-linked structure. So the 5-minute epoxies are obviously fairly simple. They cure at room temperature. There are a number of materials, a number of thermosetting polymers that will also be initiated at higher temperatures, or at least the reaction rate would increase as a function of temperature. And so they're actually, thermosetting polymers are quite interesting to examine in the DSC, and you actually get to see how the structure changes and builds as a function of temperature. So here in this case, you can see that we're looking at a modulated DSC experiment, and we're taking just a two-part epoxy, and mixing it up, putting it into a DSC pan, and ramping it up to, in this case, 175 degrees. And so what you can see is that on that initial first heat, we have a glass transition at lower temperatures. Once we get up to temperatures closer to above 100 degrees, you can see that we start to see an exotherm show up in our non-reversing heat flow. And so that exotherm that shows up there is actually the energy that's being released during that cross-linking component. But there are quite a few events that take place in that range there. But what you're really seeing is that on the second heat, the material actually it shows a glass transition at much higher temperatures. So by examining the heat capacity component, the blue curve, between the first and the second heat, you're actually getting a very good idea of how that structure has changed over time, outside of that just singular event, that singular exotherm that shows up in the non-reversing heat flow curve. Now, if we zoom in on that particular temperature range, you can see that, again, we see that exotherm in the non-reversing. But what you see is that there are subtle events in the structure that change in that time frame as well, in that temperature range as well. So you can see that the material actually, if we look at heat capacity in terms of molecular mobility, you can see that the mobility is relatively high until we get to that exotherm, until we get to that transition. We have vitrification taking place. When we cool the material back down, you can see that there's a pretty significant shift, a downward shift in our heat capacity, which is a direct translation or direct measure of the mobility of that material. So, once the heat capacity shifts down as much as it does, the molecular mobility shifts down as well. And so that's the material essentially going from a gel-type structure that's fairly mobile, fairly fluid, into a much more rigid structure at room temperature. So molecular mobility goes down. Heat capacity goes down. Now, obviously, you can see that if you were to take this material back up above that 140, 150 degree temperature range, that your mobility will go up again because your TG has shifted to higher temperatures. So now once you get above that temperature, you're going to start to increase your mobility, and you're going to get a more rubbery, flexible material. So you're going from if you were to look at the whole story from beginning to end, you obviously start with a gel-type material. You go through the cross-linking component. If you cool it back down, it becomes rigid. Once you heat it back up, it can become a more flexible material again. So really, we're looking at, we can see that singular event in the non-reversing heat flow, but it's really the heat capacity and how it ties to the molecular mobility that gives us the story of how that structure is really changing. Now, we've made mention of glass transition, or TG, various times during the presentation, but the glass transition really is a step change in our molecular mobility. So, as I described in some of the previous slides, below the glass transition, at temperatures below the glass transition, mobility is fairly low. So it's a fairly rigid material. Now, once we get above that glass transition, we allow the material to actually soften, and it becomes more fluid, more mobile. And so the baseline shift is just a measure of that mobility, rather than, again, a singular event that creates, either gives off energy or absorbs energy. Now, this is a plot here that shows both heat flow and heat capacity. Now they're inversely related, and so you can plot them on the same scale and get some measure of either of them. Now, the difference in DSC is that heat flow, and so the change in heat flow, is going to be a function of your heating rate, whereas the change in heat capacity is going to be an absolute value. So if the heat capacity has a significant change in it, it's going to be easy to detect even in experiments where you're ramping relatively slowly. So that's where looking at the heat capacity is sometimes more beneficial in looking at baseline shifts. Now, in this plot, we're actually showing the more or less how the material, or how the material is in its various mobile states or immobile states as we go up in temperature. So you can see that below the glass transition, the material is in a relatively frozen state, and so the molecules really just have the ability to vibrate. So they don't have the ability to move around, so they vibrate amongst one another. So once you increase temperature, you start to increase the mobility of those materials and give it more room or freedom of movement. So as you're into, let's say, the middle of that glass transition, you have the ability for some rotation. Once you get above the glass transition, now you have the mobility or the ability for the material to go through some transition. It's a function of the amount of energy that exists. It's a function of the amount of space that the material has to move around in. And so, the amount of mobility, or the amount of freedom that those materials have above the glass transition will most likely continue to change even as you increase in temperature. But there's almost a viscosity relationship to that material once you get above the glass transition. So in terms of measuring and reporting the glass transition, because it's not one singular event, it's not a peak that shows up that you can look at the peak temperature, you have a variety of different ways that you could go through reporting that particular glass transition. It is a range. We saw in one of the proteins in one of the previous slides that the range of that glass transition was 100 degrees wide. Now, you also need to be cognizant of the fact that the glass transition may show up as a different temperature, or different specific temperature, or a different temperature range based off of the mode of testing. So whether it's DSC or DMA or TMA, you may see a difference in the range of that glass transition. You may see a difference in the specific value. So you want to make sure that you report a glass transition with and tie it to the particular instrument that you are testing it with. But you also want to be consistent in the way you report it, whether it's going to be a half height, whether it's the onset, whether it's the inflection point. So if you're comparing from sample to sample, you just want to make sure that you're consistent in the way you would analyze it, because there are a number of different temperatures that you could choose from. You also want to be aware of that fact when you're trying to compare your glass transition that you measure to something that you may have found in literature. They may be using a different instrument. They may be using a different point on their particular curve. So you just need to be aware of that. As long as you're consistent, you can easily compare the glass transition temperature of your particular material set. So here's just an example of the magnitude of the glass transition and the amount of analysis that you could be pulling from that. The numbers are fairly widespread in this case. You could choose your your onset temperature. You could choose a half height temperature. You could choose the inflection point. So in this particular case, we are looking at the half height. But if you were looking at the inflection point, it may be different in some cases. You could also be looking at the offset. Now, again, like I said, as long as you're consistent from sample to sample, you're going to easily be able to compare one to the other. You're going to be able to say that one material has a glass transition that is higher than the other, even though the range may be slightly different for each of these particular materials. Now, the glass transition is a change in the heat capacity, which is why you can see that in your heat flow. The heat flow is a function of heat capacity, as well as other latent heats of fusion. But it's that change in heat capacity that gives you that shift in your heat flow. Now, sometimes you might see something in your glass transition or in your data set around the glass transition temperature that looks like a melt peak. And this particular peak is commonly referred to as the enthalpic recovery peak. And the magnitude of that peak is typically a function of the material and the way it was processed or the way it was stored. And so there's certainly some qualitative information that can be pulled from that. But it's commonly why we would recommend that you run a heat-cool-heat experiment so that you can see the material outside of its initial processing. You have the ability to look at the material in its raw form rather than as received form. So here you can see an example of an aged epoxy. So the first heat is the one that actually has a peak that looks like a melt. So it's commonly mistaken as a melt. But clearly, if you take the material, cool it back down, and reheat it under a known thermal history, you've given it a thermal history by cooling it down at 10 degrees a minute, let's say. You can see that the glass transition shows up fairly clearly in this case. So, this is one of the benefits that you get with a heat-cool-heat experiment. Now, the magnitude of this enthalpic recovery peak may give you some indication as to how it was stored, how long it was stored, the temperature at which it was stored. It's sometimes fairly difficult to quantify a lot of information from that enthalpic recovery peak. But being aware of it and aware that something like this may show up may give you a fair amount of insight when you're trying to work through your analysis so that you don't mistake it as a melt peak. Because the glass transition is not a melt. The glass transition is just simply a material softening. So if you want to get into a little bit more detail on the enthalpic recovery, you can see that we can use this chart here. So you can see that a material with, let's say, the same amount of amorphous material in it is held at a temperature above the TG. Now, obviously, we know above the TG, the material has all the freedom in the world to move around. So we're not there's no chance that it's going to relax. There's no chance that it's going to go through some sort of structural change unless it's a material that will tend to crystallize. But let's say we're dealing with polystyrene that has no ability to crystallize. And so in this case, above the TG, the properties are the same. Now we can process these materials in a couple of different ways and maybe store them in a couple of different ways. We can see just based off of this little chart, how the material might react in those particular cases. So you can see that if we cool this material very slowly, it has a lot of time to form the structure that is most ordered for that particular material. So in this case, let's say it changes its volume or it goes to a very low energy state. And so, if we were to hold it at a temperature below TG for some length of time, there's really very little change that would exist in that particular case. Now, if we take the same material and we cool it down very rapidly and we freeze it into a higher volume state or a higher order state, then obviously it has a great deal of time that it would have to take in order for it to relax and get to that lower energy state. And so you can see that by looking at the magnitude of that enthalpic recovery peak, you might be able to gain some understanding as to how one particular material was stored or cooled. If it's a material that was made up fairly fresh, then maybe maybe it was a function of the cooling rate that it was processed. If it was a material that's fairly old that you found at the bottom of your desk drawer, then obviously the enthalpic recovery peak is most likely going to be a function of that aging process rather than the processing of that material. Now, here's just another example of the annealing effect. You can see that this particular material is PMMA, a polymer that will not commonly crystallize, and you can see that this is the resultant heating curve after a variety of annealing times. And so the material, when it was annealed for 0 minutes, has very little enthalpic recovery peak. The material that was annealed for 1,000 minutes below the glass transition has a very large enthalpic recovery peak. So here you can see that the annealing time, the amount of time stored below the glass transition, will give you some magnitude in that enthalpic recovery peak. Now talking about thermal histories, storing and processing and so forth, you can see that here's another example, completely unrelated to enthalpic recovery, but again, the thermal history of this material gives you some insight and some changes in your particular data set. And so this is a Tolbutamide, and you can see that the material that it was as received has some processing effect or some storage effects associated with it because it has a very large peak that shows up at lower temperatures, followed by a melt or a polymorph at higher temperatures. Now, if we were to take that material and quench it from the melt, we form it into, or we force it into a particular structure. And in this particular case, we're taking a material that is crystalline to begin with, we melt it, and we cool it down very rapidly. We're most likely creating an amorphous concentration. So a large magnitude of this material is going from the liquid melted state into a frozen amorphous, frozen random state. And so the resultant plot is the blue curve, and in the blue curve you can see that there is a glass transition which is associated with that amorphous phase that we forced it into, followed by a cold crystallization, and once it goes to that crystallization, we then have the ability, or it has the ability to melt at higher temperatures. So you can see that the differences in how they're processed really can give you a significant difference in the material and how it shows up in the DSC. So again, that's commonly why we recommend that you would go through a heat-cool-heat process and that you get to control the cooling component of that material. We get to remove the processing effects, remove any storage effects, and we get to control that cool down so that if the materials and the composition of those two materials is the same, then they should give you the same result on that second heat. If the composition of those two materials are different, then they're most likely going to give you some difference in that second heat. So that's really how you're going to be able to differentiate the composition of materials with a heat-cool-heat experiment. Now, in this particular case, we're actually forcing the material into different forms with changing heating rates. There are materials that will, given enough time, will change into a different multitude of crystallization states. They're typically called polymorphs. And so you can see that in this case, at 5 degrees a minute, we're spending a lot of time at temperature. We're just slowly increasing temperature such that it goes through a crystallization, and then it has the ability to go through a variety of different forms. Now, if we start to increase the heating rate, we're not giving the material enough time to do what it really wants. We're forcing it into certain states. So you can see that as we get to higher and higher rates, the 40 degrees C per minute, the 80 degrees C per minute, you can see that we have some crystallization taking place, but we're also seeing some melt that takes place at lower temperatures, followed by another crystallization and then another melt. So you can see that we're starting to see the material from different vantage points, and it gives us some idea as to how the material is going to react at different heating rates. Now, switching gears just slightly here, the TMA, which we haven't discussed yet in the presentation, is another tool that you're going to be able to use to look at the structure of materials and how the structure changes. The TMA is actually a material that looks at more of a physical, volumetric, or dimensional component of the material. So the TMA is simply just going to look at how a material expands or contracts with changing temperature or changing environment. This is commonly used to look at what's called CTE, the coefficient of thermal expansion. You can look at materials in one linear direction, or you can look at the material in a different, a couple of different facets to see the change in each direction. If there's an X, Y, and Z direction, maybe a machine direction, you can look at the CTE and that material in different directions. So, why is this important? Well, as we're starting to create more and more composite materials, we're looking at materials that have different rates of expansion with changing temperature. I mean, a microchip or a computer chip is probably one of the most common applications for CTE determination. And it's very important that they get all of the materials that go into a particular chip to be close to one another, or at least know what kind of expansion would exist from each of the different materials, so that they don't have catastrophic failure with that particular chip. I mean, if you really think about it, you've got some composite substrate that a chip might be sitting on. You've got metal components. You've got silicon wafer components. You've got maybe a plastic cover that goes over a particular chip. Now, as a chip is used, it starts to heat up, cool down, heat up, cool down. If all of these particular materials don't expand and contract at similar rates or similar magnitudes, then obviously you're going to have one component that breaks free from another, or you're going to have the plastic component cracking, materials, multi-layer materials debonding from one another. So this is really where TMA is quite important, just to be able to match the various expansion rates of the materials. So if we look at a particular data set from the TMA, you can see that as we increase temperature, the material is expanding. At some point, it actually starts to expand at a much higher rate. So the onset point there is actually where the material has gone through a glass transition. So we have another tool that we can use to verify that there is a glass transition, along with the rate of expansion for these particular materials. Now, obviously, you're most commonly going to use materials below their glass transition so that you don't have them softening, losing their structural integrity, and flowing all over the place. So you're probably most concerned about the CTE of materials as you package them together below the glass transition. But there may be instances where you want to look at how a material would flow into a mold, or how much expansion might exist, or how much contraction might exist as it cools down from a particular mold. So, I mean, the coefficient of expansion, both below and above the glass transition, can be important items to gather from your particular material. So, the next section here is really going away from the structural correlation. We could probably spend all day talking about how structure and the various tools interact, but the next section is don't overanalyze. And this is a fairly common pitfall that we all find ourselves, is that we think that there should be something in a particular data set, and we start to look into it and we say, oh, well, this has to be this transition, and this has to be that transition, or there's something wrong with my instrument because it's giving me this particular effect. And so in most cases, the most obvious answer is the answer. It's hard for us to sometimes believe that that's the case. So we'll take a look at some features here in data sets and give you maybe some comfort that the instrument is doing what it should be doing, or the material is doing what it should be doing. So the first transition here, the first data set here is looking at the startup hook in the DSC. Now this is fairly common. It's a fairly common question as to why there is a startup hook. Why is there a deviation from the baseline at the very beginning of your particular data set? But at heating rate of 0, the heat flow is 0. And so once you really start ramping your experiment, you have to go from 0 milliwatts to some function, to some value of heat flow. And that value of heat flow is going to be a function of the material heat capacity, any transitions that may be presented in that particular material, as well as the heating rate. So a very large heating rate, 20, 30, 40 degrees C per minute, might give you a very large startup hook. If you're only ramping at 1 degree a minute or 5 degrees a minute, the startup hook might be relatively small. But it's a common feature of any DSC because you are starting at an isotherm and you are ramping at some particular rate. So it's just the start effect of any DSC. Now, if we look at some glass transition analyses, you can see that on the heating curve and the cooling curve, it looks as if the glass transition on the cooling curve is not nearly as prominent as we see in the heating curve. Now, if it's a material that has a glass transition that is reversible, we haven't changed the structure in any way, we should be able to see that glass transition on the cooling curve. And it should be just as large a magnitude, just as pronounced as it is in the heating curve. Now, we look at this particular example, and it looks like it's broadened out. It looks like it's shifted temperature. Well, it's really just an effect of that particular heating rate that we are looking at, or the cooling rate, rather, that we're examining. So if we were to plot the cooling rate or the heating rate over this entire range, you can see that we maintain our heating rate of set value all the way through the heating curve. But what you can see is that when we're starting to cool this particular material, that the cooling rate starts to diminish. We don't have the cooling capacity necessary to maintain a solid linear cooling rate. And so once that cooling rate changes, we start to see that it changes our heat flow. It's the same effect that we see with the startup hook. The same reason why we see that startup hook is that the heat flow and the resultant heat flow that you see is a function of heat capacity and the heating rate, or in this case, the cooling rate. So once the cooling rate starts to change, our heat flow signal is going to start to change as well. So it is the same glass transition. If we wanted to see these two glass transitions to be the same magnitude and the same look and feel both on heating and cooling, we would have to make our heating rate the same as what we can maintain in our cooling rate, so that we don't have to worry about a changing rate through that experiment. Now, this is probably one of the most common anomalies that we see in any one particular data set. And usually the common question is this something wrong with my DSC? And that, do I need to get service in? Well, the fact is that this is actually an effect of the material. Some materials will show this. And in this particular case, it's the supercooling of water. And so some materials have transitions that are so energetic, either exothermic or endothermic, that they're going to change their own temperature. And so the DSC is designed to monitor the temperature of the sample. It's not program temperature. It's not the temperature of the furnace. It's showing you on that temperature scale the exact temperature of that material, which is exactly what you want. You want to know what the temperature of the sample is. You do not really care what the furnace temperature is during a particular transition. So the effect that you see here is that as water starts to freeze, starts to crystallize, the transition is so high in energy that it actually starts to heat itself up. And so the loop is just that thermocouple registering that change in temperature. Now, once the transition is completed, you can see that it returns to it returns to the temperature at which the furnace is. So, it will eventually get to, back to the original temperature and back to the original heating or cooling rate. But the loop is simply just an effect of the material and how it goes through that reaction. Now, the easiest way to combat that, if you see some transition that shows up that way, is to actually take it off of the temperature scale and plot it on a time scale, so that your x-axis is now time rather than temperature. You can plot temperature on, let's say, a y2 axis and see how that temperature is changing. But what you'll most likely see is that the peak that shows up will look more natural to you. It will look more like a crystallization or a melt peak, because once the axis has changed to time, now it's just showing you the amount of energy associated with that transition as a function of time. Now here you can see that we are also plotting the sample temperature in blue. You can see right at that instance where the water begins to freeze, that the temperature does increase fairly significantly. So that's giving you a measure of how that material is changing during that reaction. Now if you integrate that particular area, the amount of energy that it uses, or the amount of energy that it gives off in that particular reaction, is going to be exactly the same whether it had a loop in it or not. So the DSC measures that amount of energy regardless of whether it increases in temperature, whether the sample increases in temperature or not. So you shouldn't be afraid of seeing that loop. It's not anything wrong with your DSC. It is really what the material is going through. This can be very important when you're looking at materials and how they're processed, and looking at maybe the kinetic nature of a crystallization process of a polymer. If you're trying to develop some kinetic model, some crystallization model of a particular material, and you are just using program temperature, your kinetic data will be wrong because you're not accounting for the fact that that material is actually changing temperature as it goes through that reaction. Another data set where we are, we're looking at the heating rate and the heating rate aberration that exists during that particular reaction. But you can see that it heats up fairly rapidly in that initial section, and the sample itself appears to cool down fairly significantly during that portion, but it's really mostly a function of it catching back up with the heating rate or the cooling rate of that particular DSC. Now here is a TGA plot, and you can see that in the TGA we can also see anomalies that show up. And I'd say that anomalies like this show up more in TGA than they do in DSC, but in this particular case you can see that there's an anomaly in the weight. This can be a multitude of a number of things. It could be that the sample is going through a fairly energetic reaction, which is going to be the case here. It could be that the sample is starting to pop and foam and fizzle, and you could be losing material up off of that particular pan. So you could see weight anomalies in that fashion. But in this particular case, again, we're plotting our data as a function of temperature, and you can see that there's an anomaly here. And it's most likely the degradation of this material is so energetic that it is probably creating almost like a rocket or propellant, such that the sample appears to be slightly heavier just at that one little instant. And so then we get an anomaly in our data set. Now, you can always look at the scanning rate and the heating rate, plot it versus time or temperature to see that the reaction is going through a fairly violent decomposition or a fairly energetic decomposition. But usually minor minor anomalies that show up in your weight signal like that are associated more with the sample going through some violent reaction of some kind. Now, another example of an anomaly in the TGA weight is, again, associated with energetic material. The energetic materials tend to be the culprits in a lot of anomalies that show up in your data sets. But in this case, it looks like, or it appears as if the temperature has increased significantly so that the furnace is out of control. But again, we're plotting this versus temperature. So if the sample is going through a fairly violent reaction, a fairly highly exothermic reaction, there's a good chance that it's going to affect the temperature that thermocouple is registering. And so that's where it appears as if the temperature increases. Now, again, the easiest way to examine this particular experiment or examine this material is to plot the data set versus time. And here you can see that if we're plotting every single point of that experiment versus temperature, and our data sampling rate is 1 point every half a second, you can see that there's only 1 second between the time it is in control to the time that it goes out of control. So it happens very rapidly. If we take that same sample, plot it versus time, you can see a more normal look to a weight curve. You can see that it really only takes a second for it to go through that degradation, or maybe a few seconds, a handful of seconds for it to go through the degradation. So it's that degradation process is so highly exothermic and energetic that it is being registered. That energy is being collected by the thermocouple that's there, right next to the sample. So again, it's giving you a good indication of what the material is really doing. It's not giving you a furnace temperature. It's not giving you a program temperature. The thermocouple is telling you exactly what that sample is doing. Sometimes we just have to look at it from a different perspective in order to see what's really going on. Now here's another example. This is more common in a Q500 or a TGA that has a thermocouple sitting above it. But again, we have another weight anomaly that shows up. And so, like I said, typically the weight anomalies are something that the sample is doing more so than the instrument causing a failure or creating a failure. And so you can see that our weight signal is out of control, our derivative signal is out of control, and it appears as if there's something strange going on. If we zoom in a little bit further, you can see that if we were to take out this little anomaly in the weight signal, it looks like that the data is fairly continuous before the peak and after the peak, which makes me think that the sample itself is doing something, is touching something inside there, or maybe that someone bumped the instrument, and that's what created this anomaly in the weight signal. If it were really a significant weight loss at that very instant, then the weight wouldn't come back to where it was before this anomaly occurred. It's not going to lose and gain weight that rapidly in the TGA. The TGA is going to monitor weight gains and weight losses, but nothing that happens in that short a time span. So if we investigate it a little bit further, plot some other signals here, we can plot the heating rate, we can plot the weight signal and the derivative of the weight signal. You can see that the temperature and the weight signal are both being affected by this anomaly, which gives me a good indication that the sample may be foamed up or bubbled up, or it started to flow and it ended up touching the thermocouple, so that it's affecting both the temperature that the thermocouple is reading as well as the weight signal, since now it has a tie. The sample pan isn't just being balanced there. It could be touching the thermocouple, it could be touching the side of the furnace. So those are all things that you have to keep in mind when you're going through these particular data sets. But again, if you don't want to spend too much time analyzing these data sets, assuming that there's something either wrong with the instrument or something wrong with the material. It may be telling you exactly what the material is doing. You just have to look at it from a different perspective. Now here again, we're looking at a simpler curve on DSC. We're looking at modulated DSC. This is most likely a cured or an epoxy going through a curing exotherm. This is somewhat of a universal analysis trick or a universal analysis component. We discussed this a little bit right away in this particular segment, but it's really just a function of the software plotting all three curves here on a maximum scale. And so you can see that the scaling between the three curves is not the same from Y1, Y2, and Y3. If you were to plot this particular data set on a more common scale, place all three variables on one axis, you can see that the reversing heat flow curve really doesn't show us anything. It's really a curing exotherm, and that particular curing exotherm is always going to show up in the non-reversing heat flow. And so any anomalies that we see, any variation or in the reversing heat flow is just minor. It's insignificant in this particular case. So again, you got to keep everything in perspective. Make sure that you have all of your scaling normalized, as we've discussed both here and at the beginning of this particular section. Now we've looked at this a little bit before, but again, we see that a fresh sample versus an annealed sample of PMMA, the annealed sample appears to have a peak. It could make you assume that this is a melt rather than a glass transition. Heating up a fresh sample shows you that it's a nice clean glass transition. You have a couple different options. It's either a heat-cool heat experiment, or in this particular case, we can run a modulated experiment, and then we can see that in that modulated experiment that our reversing heat flow shows the glass transition. The non-reversing heat flow shows us that enthalpic recovery peak, as it should. So, again, there are a couple of different ways. Modulated DSC will allow you to get more information from that material in one single run in the first run, whereas heat-cool heat is an experiment that you can run on that material if you don't have modulated. And we'll give you information about whether that was really an enthalpic recovery peak or whether that was something else that you need to investigate further. So we've talked about data. We've talked about not overanalyzing. We've talked about a majority of the structural correlations that go with that. Now, the next section here is really just looking at a few features that exist in the software that many people aren't commonly aware of, but can be powerful when you're trying to collect information and generate reports and so forth. And so the software that we use for all of the TA Instruments equipment is fully compatible with a lot of other Microsoft Office applications. I mean, obviously you can take plots, copy them, paste them into PowerPoints, paste them into Word documents so that you can present them that way. But there are also a couple other tools that we use that that incorporate the results that you might collect from a particular plot and throw them into Excel so that you can do some post-analysis, copying and pasting results and using them in some other application. So there are a number of different things that you can use to take the results that you've collected to the next level. So you can look at a lot of your results in a spreadsheet form. In universal analysis, you have the ability to go to a spreadsheet view. You can see your results in a spreadsheet view. You can choose the items that you want to be exported into that particular spreadsheet view. And then it will open up Excel. Assuming that you have Excel on your computer, it will take the results that you've collected on your plot and throw them over into a spreadsheet in Excel so that you can then work with them in that fashion. So there is a tie between universal analysis and Excel. If you're collecting, let's say you're collecting 10, 20, 30 different formulations, you have a multitude of experiments, you're looking at glass transitions or peak integrations on each one of those 10 or 20 plots. Instead of just jotting them all down and then retyping them into Excel, you have the ability to put them into an overlay and throw those results over into an Excel spreadsheet. Now, staying within the Advantage realm or the Q series realm, we have macros that are available. The macros, they work similar to an Excel macro in such that they will run through a segment or a section of commands that you have collected, so that if you're working over redundant types of analyses, you can create a macro so that it will do the same analysis over and over and over on a multitude of data sets. Now, it's not commonly smart enough to be able to do all of your work for you, but if you have data sets that are very similar to one another, you could certainly create a macro that will work through the same general actions over and over. So it can save you some time. There are some capture tools that allow you to examine or collect the actions that you have done on one data set, and then you can use that macro, those collected segments, to reanalyze other data sets. So you have some functionality with macros in that regard. Within Advantage, you also have the ability to do an auto-analyze. And so in that sense, you can create a macro that does some of the analysis for you. If it's a simple type of analysis, it may do all of the work for you. But you have the option to do an auto-analyze. So when you're creating your method, you have an option in that method to do an auto-analysis. In that case, you would select auto-analyze. You would select the macro at which you want it to work through at the end of a particular experiment. And once it finishes collecting all the data, it will go through the actions that are in that particular macro. Now, Trios utilizes something similar in terms of tabulating results, but it uses something integrated within the software. So instead of utilizing Excel, some people may not have Excel on their computer. So what Trios has done is actually allowed you to create an analysis document. You would create a new analysis document similar to the way you would create a new overlay document, but you would tabulate results. They can be in individual files, they can be in overlays, and you can actually send all of those results that you've tabulated and throw them into this new analysis document or into the analysis document. And it's much more flexible, more power to it, simply because you're not having to rely on Excel. But the other nice thing about it is that you have the same plotting and formatting abilities that you have within all of your other data sets that you've collected in Trios. So, being able to change your scaling, to zoom in, to tabulate results, to see trending type data, you can do all within Trios now. So you don't have to rely on Excel, rely on the plotting and graphing components of Excel. You can do all of that functionality within Trios. And again, you have full functionality of variables and scalars and so forth. So there's much more power to these analysis documents if you're really tabulating a lot of results and you want to be able to generate reports, present these to an outside customer. Really there's quite a bit of additional information in terms of utilizing Trios and utilizing universal analysis and Advantage to their fullest capabilities via our website and the TA Tech videos that we have listed on our website. They're also available on our YouTube channel. So you have the ability to see little tips and tricks on how to use the software, how to use the instruments, how to calibrate, change hang down wires. There's a whole multitude of information available to you, all via the web. If you don't know where to start, first start at the TA Instruments website. You can also find us on YouTube, as I mentioned before. Now, this particular presentation is really designed to get you started in terms of collecting some good data, working through your data analysis. But if there's always ongoing education opportunities for you out there. If you need to sit through a training session, or you want to ask specific questions, or you want more hands-on sorts of training, there are a multitude of resources for training purposes. So if you go to the TA Instruments website, you can see that there's a list of training courses available that you can have either on-site training or in-house training. There are tech tip videos. There are applications and theory classes that are given 6 to 8 times per year here at TA Instruments. There is also the opportunity for you to have a TA product specialist come to your site if you want to train a multitude of people. If you want to have hands-on training with your materials and you can't bring your materials in-house. So there's again a whole nother level of educational resources available to you through applications training. On the website, there are also opportunities there are quick start courses that can guide you through different facets of data analysis, of data collection, how to use universal analysis, how to use trios. That gives you a much more in-depth instruction over what we've covered in this particular training session. And again, I'll mention the TA Tech Tips. They're quick videos that give you, tips on how to do, small tasks. And hopefully it's just a small question here and there that you're having trouble with, and the tech tip will get you, get you going into the next phase, whether it be sample loading, pan loading. So these are relatively quick, but they're extremely powerful and very helpful. And finally, really, if you need help, and you've gone through the courses and you've sat through the seminars and you've looked at the TA Tech Tips and you still need help interpreting data, or you need help figuring out how to do a certain task with either the software or the instruments, or calibrating the instruments, there's always the hotline that's available. And so you have a phone number that you can call between 8 and 4:30 Eastern Time, and there's always an email address that you can send questions to as well. Obviously, the email questions are only going to be addressed between 8 and 4:30 Eastern Time, but at least you can send data sets in, send presentations, send pieces of information that might help you, or you might need help in interpreting. And if all else, you can check out TA Instruments website. That should be able to guide you to either training courses, quick start courses, tech tips, and so forth. So there are plenty of resources out there available to you. Don't ever feel lost when you're working with TA Instruments. And so that will conclude our course. Thank you for your time. A version of this course will be available online, as well as the entire seminar available on TA Instruments website. Thank you for your interest.
This concludes the strategies for better thermal analysis data from TA Instruments. Be sure to go back and view the first 2 segments on instrument fundamentals, sample preparation, and data analysis. These and many other resources are available on the TA Instruments website. Feel free to ask any questions you may have in the Q&A window, as well as explore the additional resources provided by clicking the resource widget. From all of us here at TA Instruments, thank you for your interest.